All right, in chapter 10, we're going to talk about correlation and regression. In this presentation, we're just going to cover sections 10.1, 10.2, and 10.3. In Stats 2 in the summer, we will talk about 10.4 and 5, which is multiple linear regression and logistic regression. Okay, so let's go back to our friend, the flowchart. We've talked about describe, we've talked about compare, and now we're going to do explain relationship between two variables or predict. And when we want to look at the relationship, we use correlation, and when we want to do predictions, we use regression. Okay, so first we'll take a look at correlation. Correlation is a statistical technique that's used to measure and describe a linear relationship between two variables. In it, the variables are not manipulated. It requires two scores for each individual, an X and a Y. It can be listed in a table or as a scatter plot. It's sometimes referred to as the Pearson product moment correlation coefficient, and it is denoted by the lowercase r. There are other correlation coefficients for nonlinear or other types of relationships, but here we're going to cover the linear correlation coefficient. Okay, so the requirements. First, you need to have a sample of paired data, so X and Y need to come from a simple random sample of quantitative data. Visual examination of the scatter plot shows a linear pattern. And a note about bivariate normality. So at a fixed value of X, the Y data are normal, and at a fixed value of Y, the X data are normal. And we're just going to assume normality for a sufficiently large sample, for example, greater than 30. And then one thing to note is that outliers radically affect the results. So you want to check to make sure if you do have outliers that there aren't errors, that they aren't errors. If they're true data, then, that's your data. Okay, characteristics. So the strength of the correlation, the strength of the relationship spans between -1 and +1. And so the strength of the relationship has to do with the magnitude, not sign. So a correlation of -0.87 is a stronger relationship than +0.80 because the number is larger, it has nothing to do with the sign. Scale. If all values of either variable are converted to a different scale, it does not change the correlation. Interchangeable. It doesn't matter which is X or Y. It doesn't change the relationship. It will change the scatter plot, but it won't change the relationship or the magnitude. Direction. The sign of the correlation, positive or negative, denotes the direction, not magnitude. So same thing what I said up here. And then the form is for linear relationships. Okay, so for example, if I go up and to the right, I have a positive correlation, and this is a correlation of 0.895, which is pretty strong. It's close to +1. Here I have a negative correlation, and you can see that it's 0.97, which is a larger magnitude than this one, and it doesn't matter that it's negative. This would be considered a stronger relationship than this one. Here, when we just have this blob of this scatter point, which is just a blob of points, we have 0.074, which is close to 0, so we'd say that's no correlation or there's no relationship. And then here we have a curvilinear relationship. If I were to drop a line among these data points, it shows that it's not very strong, but if I were to use a different correlation coefficient, I would capture more of this relationship. Okay, cautions. Remember, correlation does not imply causation. You need a true experiment for that. The value can be affected by the range of scores, and the value can be affected by outliers, and it should not be interpreted as a proportion. Okay, so let's look at example 1 on page 448. This is a very tiny data set. We only have 5 points. And so therefore, we're going to just kind of ignore the normality because we don't have a very large sample size, but we're going to do it for the demonstration. So what's my research question? Is there a relationship between pulse rate and white blood cell count? So I have my pulse rate in this column and my white blood cell count in this column. And for each of these rows, this is an individual. So we have this person's score here, and this person's score here, same person. Okay, so we enter our data, Now first we want to look at the scatter plot. There's several ways to do this, but we can go to Graphs, Legacy Dialogs, Scatter Dot, pick Simple Scatter, click Define, move over our variables, and click OK. We're familiar with this. And we get this scatter plot, right? And it's not very easy to tell what's going on because there's so few data. Mentally, I tried to draw a line through the data, or I cheated and used the computer to draw the fit line, and you can see that it hugs these 4 points up here, and this guy is an outlier. Okay, so let's see what the coefficient is. So we're going to ask, is there a significant relationship between pulse rate and white blood cell count? Our null hypothesis is that there is no relationship between pulse rate and white blood cell count, and our alternate is that there is a relationship between pulse rate and white blood cell count. And here, you know, we've been writing our hypotheses with the Greek letter, and this little P looking thing is actually a rho, which is the Greek letter for R. And so we would say rho is equal to 0, rho is not equal to 0. But we're not going to use this anymore, we'll just use words. Okay, so another note about degrees of freedom. The hypothesis test says degrees of freedom defined as n minus 2. Okay, so in a sample of only 2, they both sit directly on the correlation line, right? So there are no degrees of freedom, and R would be plus or minus 1, depending on the direction. So because the first 2 points present a perfect correlation, the sample correlation is free to vary only when the data set contains more than 2 points. Therefore, degrees of freedom is going to be n minus 2. And we'll talk about that when we talk about reporting. So how do we do it? We go to Analyze, Correlate, Bivariate, move our variables over. So I go to Analyze, Correlate, Bivariate, move these guys over, pulse rate, white blood cell count, leave everything like it is, and click OK. We're not going to use the bivariate with confidence intervals for such a small sample, but if you're doing a study for your own research and you would want to use it, you would do it the same way. It's just now we have correlate, we have bivariate, and we now have bivariate with confidence intervals. Okay, so I kind of have a lot going on this slide. First thing I want to call your attention to is the output. Okay, so we see we have pulse rate and white blood cell count, pulse rate and white blood cell count. Correlation is calculated using a matrix. And because it's a matrix, what's in the upper right-hand corner is replicated in the lower left-hand corner. Pulse rate correlated with itself is a perfect correlation. So that's where you see the 1 here, same with white blood cell count. So when you're reporting, you just look at the upper right-hand corner or the lower left-hand corner. And we can see that the correlation coefficient here is 0.41. The significance is 0.499, so it is not significant, and our sample size is 5. We would write it out as results indicate that there is no statistically significant relationship between pulse rates and white blood cell counts. R of degrees of freedom 3 is equal to 0.405. The P is equal to 0.499. AMA, I have not been able to find specific directions, but it usually just reports the R and the coefficient. And my understanding would be that you would only report significant correlations because it doesn't give the p-value in the AMA manual that I have. Anyway, so we'll just stick with the APA. Shameless plug, just to show you what reporting out statistics looks like. This is from a paper I wrote with my dissertation advisor, Paul Mooney, when I was in school. We looked at general outcome measurements of academic language in science and social studies. You can see the citation here. We have all these different measures, and we're correlating these, so fall and winter, fall and spring, with all of these things. And you can see that I only report the upper right-hand corner. So this was for science, and this is for social studies. And then I have a note, all correlations are significantly different than 0 at the 0.01 level except where marked. This is given in APA format. But I just wanted to show you what a correlation matrix looks like. It doesn't make any sense to repeat it, so you just give either the upper right or the lower left corner. Coefficient of determination is a different effect size. Since correlation shouldn't be interpreted as a proportion, you can square it to get the coefficient of determination, which can be treated as a percentage. You don't typically do this for correlation, you do this for regression. And we'll see that. But you could measure the proportion of variability in one variable that can be determined from the relationship of another. So you square the R value and multiply it by 100. So here we wasn't significant, and again, doesn't make sense to report an effect size when you don't have significant findings. But if you wanted to know what's the portion of variability in one variable that's explained by the other variable, you would square it. And so you could see that 16.4% of the variability in red blood cell counts is accounted for by pulse rates. I say it works just like the eta and partial eta squared interpretation. Okay, so this is just kind of a summary of what I've already been saying. The results, if we had significant findings, we would write it out like this. Results indicate that there is no statistically significant relationship between pulse rates and white blood cell counts. Write it out this way. The coefficient of determination, R squared, is equal to 0.164. Therefore, 16.4% of the variation in pulse rates is accounted for by white blood cell counts. Okay, simple linear regression. It's called simple because there's only one independent variable. When we have more than one, we call it multiple linear regression. So linear regression is a statistical technique for finding the best fitting straight line for a set of data. We have different vocabulary in regression. Our independent variable, we can still call it independent variable, but it's also referred to as a predictor variable or an explanatory variable. The dependent variable is also called the criterion variable or the outcome variable. We're going to look at the linear relationship, which can be explained by this equation. Y hat is equal to beta naught plus beta 1 x. The beta naught is the y-intercept, beta 1 is the slope, and the y hat is the response, the outcome, or the dependent variable, and the x is the explanatory, the predictor, or the independent variable. You may recognize the point slope formula. Y is equal to mx plus b, like we learned in algebra in high school. It's the same formula. We're just using it and giving it different vocabulary. So the line of best fit through the scatter plot is really what we're calculating when we calculate regression. The best fit line, y should have a little hat, equals beta naught plus beta 1 x. You can see that each of these plot points, we use least squares regression. So we calculate the closest line between all of these points, and we draw it, and then the distance between the actual point and the line is called a residual, or also called error. So how well a set of data points fits a straight line can be measured by calculating the distance between the data points and the line. Using this equation, it's possible to find the predicted value of y hat for any x. The error, the distance between the predicted value and the actual value, can be found by y hat minus y, also called the residual. Because some distances may be negative, each distance should be squared so that all measures are positive. Okay, we don't need to really worry so much about this, we just need to know how to evaluate the output. So it works the same way as correlation. You need to have two scores for every individual. You need to have one score, which is the predictor, the X score, and the other score, which is the Y. So you need to have one for each. So you're not just predicting from nothing. You have to have a data set that has both the predictor and the outcome, and then you're going to use that data set. Again, remember, the whole point of inferential statistics is to generalize back to the population. So you're using your sample data to generalize to the population. Now it matters who is X and who's Y, so you can't, these aren't interchangeable. You say you regress Y on X, which means you are projecting Y onto the space spanned by the X variable. We don't often hear it referred to this way, but I just wanted you to see it because sometimes you do. Okay, so there's two parts of regression, and this slide came from when we used to do these by hand. The predicted variability and the unpredicted variability. The predicted variability goes in the numerator, so you have the sum of squares regression, which is calculated by the R squared times the sum of squares of Y, and there's a whole long calculation to do it that way, and then the sum of squares residual is in the denominator, and you calculate it out this way. So you have numerators degrees of freedom and denominator degrees of freedom, just like you have in ANOVA. And for a simple linear regression, the numerator is always going to be 1 because you only have two variables. And then the degrees of freedom for the denominator is your sample size minus 2, just like in correlation. And then the residual is the difference, like I've said, between observed and the observed value of the dependent variable and the predicted value, y hat, is called the residual, which is denoted as E. And each data point has one residual. Okay, so now we can do hypothesis testing. I'll spare you the details, but the output of regression equation is very much the same as that of ANOVA. They both have ANOVA tables. The only difference is in the x variable. In ANOVA, the x variable, the independent variable, is categorical. So I had to kind of dig deep to think of three groups. Difference in scores between Stats 1 online class versus Stats 1 face-to-face class in the morning and Stats 1 face-to-face class in the evening. So three groups. And in regression, the x variable is continuous. Say, for example, a score on a quiz to predict the final quiz or the final grade. But in reality, you can also do regression with a categorical variable, but then you would need to dummy code. And I will explain that when we get to multiple regression. Okay, so in ANOVA, you see you have mean square between and mean square within. It's an F statistic with numerator and denominator degrees of freedom. Same thing, just different vocabulary. We just now call it mean square regression over mean square residual. So let's do hypothesis testing. So our research question 1 is, does percent body fat predict BMI? So we're going to state the null in our alternate, and we're just going to do it in words now. Percent body fat does not predict BMI. And percent body fat does predict BMI. Our alpha level is always 0.05. We'll calculate this test statistic using SPSS, and then we'll evaluate our output. So we're going to use the body fat data set. Now this can get a little bit complicated, but there are some assumptions that must be considered. First, that the residuals, not the original data, the residuals are normally distributed. Then that there are no influential points. What an influential point is an outlier that greatly affects the regression. We're going to use Cook's D values, and anything that are greater than 1 are considered influential and problematic. And then that the residual plot, the graph of the x and y minus y hat values, show no pattern in the data. We want a roughly rectangular blob of data points within plus or minus 3 standard deviations along the x and y axes. I'll show you how to do all of that. Okay, so let's check the scatter plot and correlation. So when I create the scatter plot with BMI and percent body fat, you can see I have a pretty strong positive correlation with a few outliers, right? We've got a few. The correlation between the independent variable and the dependent variable is strong and significant, so it's possible there'll be a significant prediction. So we see we have 0.73, and it's 2 little stars means correlation is significant at 0.01 level, two-tailed, so we have highly significant correlation. So yes, we can use this as a predictor. So we'd go to analyze, come down to regression, slide over to linear. We'd put BMI into our dependent variable and percent body fat into our independent variable, and then we click statistics. This will pop up. We're going to click estimates. We're going to click confidence intervals, and it auto-populates 95. We're going to click model fit. I actually think that's already, I think the estimates and model fit are already checked. And then we're going to click descriptives. Then we'll click continue, and then we'll go back and do plots. Okay, when we get to plots, we're going to do Z predicted and Z resid. So we're going to bring this one down and this one over. So we have this one as the X and this one as the Y. And I just always do it the same way and just kind of think of this little crisscross. And that's the way I remember it. And click the normal probability plot and then click continue. And then we're going to go to save. And then the only thing we want to click is Cook's. So we can do that. We click continue. It brings us back to the original thing. We click OK. We're going to check our assumptions. So standardized residuals in Cook's D. We want to see that the standardized residuals are not greater than plus or minus 3. These work like z-scores. And we'll get in our output relevant information to evaluate Cook's distance. We want the maximum value to be less than 1, indicating that there are no outliers that are seriously affecting the regression, which we call influential points. And then we'll see the residuals also in the resid plot. Okay, so we get a lot of output, and let's begin with the residual plot. And so what we want to do is we want to make sure that we're within plus or minus 3, right? So you can see we have plus or minus 2 is where the bulk of these data points are. Here's about 3, here's about positive 3. We've got this guy, and this guy goes all the way up to 8, right? Most of it's within plus or minus 2. So yeah, we may have a few outliers, but it depends on Cook's D. So we'll just keep going. Our predicted probability plot looks normal, so we have we kind of hug the line, so we're just going to keep on going. So then we get descriptives, correlations, and variables entered and removed. We just keep on trucking. None of this is new to us. Okay, now we have the model summary. Now, ANOVA table looks just like the ANOVA table when we did ANOVA, but here it says regression of residual and total instead of between, within, and total. We look and our omnibus test is significant. Yes, it is a significant predictor. We can see that the correlation, so it gives us this capital R, which is the correlation. If you look, it's the same as this, 0.726. When you square it, it's 0.527. It's the coefficient of determination, i.e. the variation in BMI in the sample data predictable by the simple linear regression model with percent body fat as the predictor. Therefore, or thus, 52.7% of the variation in BMI can be predicted by percent body fat. And then we would write up the F statistic this way. So degrees of freedom 1, 250 for the residual. We write out our F statistic here, and then our P is less than 0.01. Okay, now we go to the coefficients, and our constant, see in SPSS they call the constant is the y-intercept. That's our beta naught. And our percent body fat, that's our predictor, that's our beta 1. So this is the predicted change, the slope, the regression coefficient, which is beta 1, and the constant is our y-intercept, which is beta naught. And each of these get tested. They're both actually significant. So our t-value, if you remember t-values, 48 is huge, 16 is pretty huge as well. So each of these are significant predictors of the outcome variable. And then we have the residual statistics. You can see that the standardized residual is between -2 essentially and 7, right? So the upper end might be somewhat problematic. But then we look at our Cooks and we're between 0 and 0.5. So we're less than 1, so we're okay, no influential points. Okay, and so when we look at these coefficients, what this means is that when body fat is equal to 0, the BMI of the would be the value of the constant, so 19.3. So if the percent body fat, if our predictor were 0, the constant would be the predicted value. And for every unit increase in 1 percentage point in body fat, the BMI would increase by 0.32. So this coefficient, every unit increase in percent body fat, so if I went from 0 to 1, I would multiply it times 0.31 and add it to 19. If I had BMI of 2, I'd multiply it by 2 and add it to 19. If I had a BMI of 3, so forth and so on. And so that's how we use our predicted equation. Okay, so back to our question. We have our null and our alternate. I should have taken these out. We're going to state our conclusion in APA format. And we could do it in AMA, but we'll just do it in APA for now. Okay, so findings indicate that percent body fat is a significant predictor of BMI. F of 1 of 250 is equal to 278.9, P is less than 0.01, R squared is equal to 0.527. Approximately 52.7% of the variance in BMI can be attributed to percent body fat. And then, not so important for a simple linear regression because there is only one predictor, but when we get into multiple, you would do this for each of your predictors, so we're just going to do it each time. Examining the predictor, we see that percent body fat is a significant predictor of BMI. T is equal to 16.7, P is less than 0.05, and the confidence interval. And that came from here, 16.7, less than 0.05, and then the confidence. So now we can go back to our prediction equation. So if I write out my prediction equation here and I plug in my values, so 19.3 is my slope, my beta naught, 0.317 is my beta 1, and then my x. Based on the regression equation, what would be the best prediction of a BMI for a person with percent body fat of 25? So then I just plug it in. I'd write it out and then put the new value, which is 25, multiply that out, add it, and get a BMI of 27.2. In order to do these predictions, we have to have data for both the outcome and the predictor variable, and then we use our sample to predict future body fat. And the bigger our sample is, the better our predictions will be. Okay, briefly, we'll do another one. So we're going to use a different data set. This is grades on 3 exams and an overall course grade or final grade for 233 students during several years for a statistics course at a university. I got this from a website. So does exam 3 predict the final grade in a statistics class? So the research question is, does exam 3 predict the final grade? The null is that the exam 3 does not predict the final grade, and the alternate is that it does. Alpha is 05, we'll calculate this test statistic. We're going to remember, check assumptions. Residuals are normally distributed. We're going to check Cook's D for influential points. We want to look to be sure that our residual plot is a roughly rectangular blob of data points. Again, we do analyze, regression, linear. Move final grade to the dependent. Move exam 3 to the independent. Click statistics. We're going to click estimates, confidence intervals, model fit, descriptives. Then we're going to go to plots. We're going to do the crisscross, Z predicted in the X and Z residual in the Y. Then we click normal probability plot. Then we're going to click save and just go click Cooks, go to continue, go back, click OK, and we get our first assumption. So you actually have to scroll down a little bit in the output because this doesn't come first, but we check this first. And so we can see we have a little bit of a, I don't know, I wouldn't call it a fan pattern, but we see we have more of a concentration of data points to the right, a few problematic points that are beyond point -3 to the right. Everything's kind of behaving well within the right edge of this, but within 2 standard deviations. This goes down to -4, and so for the most part it's very subjective. Like I say here, we're just going to keep going. Got normality. This is the same thing, and so we get to our model summary in our ANOVA table. First, let's look and we see, yes, we have a significant predictor. Our F statistic is 211.4 with 1 degrees in the numerator and 231 degrees of freedom in the denominator. We'd write it out like this in APA. I'll show you in a minute in AMA. This capital R is also, it's the lowercase r, it's the Pearson correlation. It's a little bit lower than the other one, it's 0.69. And our R square is 0.478, so 47.8% of the variation in the final grade can be predicted by exam 3. Got this busy slide. Again, we have our constant and our beta naught and our beta 1. And what this means, this is a little bit conceptually more easy to understand than the BMI. So what this means is if you got a 0 on your third exam, you're going to get a 39 on your course grade. And so for every unit increase, you would increase. So if I got a 1 on my third exam, I'd get 37 plus 0.461. If I got a 2, I'd multiply it and add it to that. If I got a 3, etc., etc., etc. Okay, here's the predictor for that particular independent variable. Since there's only one, gives you the same finding, but when you have multiple regression, we'll look at each one individually. Here's our confidence intervals. Let's check our assumptions. Our residual is a little misbehaved, just a little beyond point -3, so it's like -4 and 2, but it's okay. And then our Cook's is less than 1, so we're going to just keep on trucking. All right, so let's remember our research question: does exam 3 predict final course grade? We'll state the conclusion, and here I give you AMA and APA. Findings indicate that exam 3 is a significant predictor of final grade, and we write it out. Approximately 47.8% of the variance in the final grade can be attributed to exam 3. Examining the predictor, we see that exam 3 is a significant predictor of final grade, and I report out the T statistic. All right, again, we'll remember the prediction equation. All of this is the same. Now we're going to do the prediction equation. If you had gotten a 75 on your third exam, what would be your final grade? And again, this is based on a data set for which we have all of the data. So say we have, well, we know our sample size is 233, and so based on those 233 participants for whom we have exam 3 and the final grade, using that and generalizing back to the population of all the people who took those statistics class at that particular university, if someone were to walk in with an exam 3 value of 75, what would be their projected final grade? And so I would take my coefficient and plug it in, and then I plug in 75, and I would get my overall my overall final grade would be a 72, so a C-. Okay, so remember, we've looked at ANOVA and we've looked at regression, which both use ANOVA source tables. One calculates the F statistic using mean square between and mean square within, and the other by mean square regression divided by mean square residual. So what's the difference? The independent variables. ANOVA looks at differences in groups, so the independent variable is categorical. So is there a difference between, or among rather, freshman, sophomore, junior, senior? So 4 groups. Regression looks at prediction, so our independent variable is continuous, like the exam. Does this exam predict that? Does pulse rate predict white blood cell count, etc.? Now you can do regression where you have a mix of continuous and categorical predictors. And when we get to multiple regression, I will explain that in much more detail. Okay,